Actually, first session we will start for fluid mechanics, and we stop at study for stabilities of bodies, buoyancy force, correct? And we study another things like viscosity, like bulk modulus of elasticity, like vapor pressure, some simple definitions like velocity, acceleration, specific gravity, specific weight, power, force, work, correct? So today we will continue for second part for fluid mechanics. We will start by classification for fluid. When we go to classify the flow, we classify the flow from different categories, and this flow, each category mainly not related to others. So, for example, if I said to you, for example, for first category here between steady and unsteady, if I tell you this flow is steady, it's not by default, for example, it is laminar or it is uniform. I'm going to second category direct and select one. No, each category, it depends on parameters. Okay. One of the major variable control to classify different categories here for this type of the fluid flow, is velocity. But we study velocity with different parameters. According to the other parameter, we study this velocity with them. We go to classify the flow in different categories. Start first, for example, for steady and unsteady flow, and the third one here, uniform and non-uniform. Many confusion happen between these two, especially between these two, steady, unsteady, and uniform and non-uniform. We're confused all the time. If the flow is steady, it is uniform by default. No, it's totally different. Why? Actually, the velocity is the function of two things. Function with time and the function with distance or displacement. Okay? If we study the velocity respect to time and the other parameter is constant, we classify the flow for one of these categories. Which one? This one. If we classify the flow with distance, with displacement, we classify the flow for this category, not the same this. It means if the velocity, we study the velocity with time, should be the other parameter keep constant. It means if we have a flow in pipe like this, for example, this flow I study at certain x, and I study here at the certain x constant, not a change x, but I study the velocity what happened with time, at time equal t1, at time equal t2, at time equal t3, and so on. But still all we study this at same position. This classification is related to classify the flow steady and unsteady. If the velocity here not changed with time, non-response to velocity with time, the velocity with time constant, the rate of change of velocity constant with time, it means this flow is steady. But if the flow velocity change it with time here in the same position, it means this one is unsteady. Unsteady. So if velocity changes with time, this unsteady. If not it changed with time, this is steady. But be careful, we study flow at a certain position. Clear? Okay. Our next one, uniform and non-uniform. In this case, we fix a time. It means I measure the velocity on the same time. But what is different? Different is I measure this velocity at different position. At x equal x1, at x equal x2, at x equal x3. At different position, but all I measure at time t equal t. Time t equal t. I measure here velocity profile, measure velocity here, measure velocity here. If the velocity not changed with different position, it means uniform flow. If it change, non-uniform. Means I can present it like this mathematically, partial v partial x equal 0, not equal 0. Equal 0, it means uniform, not change with displacement. Not equal to 0, non-uniform, changed with displacement. This two is going to be confused a lot. Okay? Okay. We will see some question related for this, how this question coming in the exam. Okay? Third classification. Laminar and turbulence flow.
So
Laminar
uniform means it is a change in time,
not
velocity.
not related to time.
No, sorry. This it is equal to 0 means it is uniform, right?
Yes,
Okay, thank you.
but what is this equal to 0? That change of velocity with different displacement at same time.
Same.
Okay, same time. It means not study at time. No. I fixed the time. Now in instantaneous. Okay, I just measure and instantaneously what is the velocity at x equal x1, x2, x3, and check if this velocity is the same, velocity profile same. For example, here, it is the velocity profile like this here. Here is the same, here is the same or different. Value of velocity same or different. Value of velocity same or different. Okay. Laminar and turbulence flow. Laminar and turbulence flow, we can know this directly if see the flow just by eye looking. You can know this laminar or turbulent approximately. Okay. Laminar, it means the layer of the flow is going together coherent. Is going to together coherent. But turbulence, no. If the flow is going in a straight line, what you suggest? Laminar or turbulence?
Laminar.
Laminar. If the flow going in zigzag, but still layers going together, but going zigzag, not going straight, going zigzag, but all layers going together, moving together.
Laminar.
Still laminar.
Laminar.
Clear? Still laminar. I will see this one here. We can check that. This is steady unsteady flow. Okay. This uniform and non-uniform flow. And he mentioned here what? The flow can describe as steady uniform, steady non-uniform, no problem. Steady uniform, unsteady non-uniform, all is accepted. This case here is important. Many questions coming for this tricky questions. I think I bring it in exams this session, but maybe not the exam today, maybe one of the next exams. But I bring in the exam, by the way. He talk about here this case is all the time unsteady, but maybe uniform or non-uniform according to the exit at the orifice side. Okay, for uniform and the non-uniform, I think is clear. For this one, the pipe, no change in diameter. It means almost the velocity not changes. The profile is going to the same, no change in the profile of velocity. This is what I see. But here is we have a change contraction. It means the velocity by logic, it is a change. It means the profile is a change. It means non-uniform flow. So the flow, if the pipe like this is uniform, if the pipe like this is non-uniform. This is clear, okay? But this is steady or unsteady. Normally, for any case, should be mentioned inside the problem itself, mention direct and clear this flow is constant rate or not constant rate. Okay, to be aware, this is steady or unsteady. One of the cases not mentioned in the word, in the sentence, and they can get it from the figure, this one of these cases, this case. You can deduce this case is steady or unsteady direct. Otherwise, you can't from the figure to just imagine to steady or unsteady. It should be mentioned direct in the sentence. But here you can imagine. Why is this case? Check with me. The flow here is going down. Decrease. The level is decreased. We study today's session, but after some slides, continuity equation, and after that, Bernoulli equation. Bernoulli equation, it is the function direct between velocity and pressure and elevation. If you apply Bernoulli equation in this case, for the case of the tank, and what is the velocity here at the exit, how to calculate the velocity at the exit here at the orifice, we will find at the end the velocity equal to root 2gh. 2 is number, g is constant. It means the only variable is h. It means the velocity, it is not a function, it is not a constant, it is function for what? For h. So if h for this tank constant, it means the velocity here not changed with time. After 5 minutes, no problem, the same velocity. 10 minutes, the same velocity, and so on. It means it's steady. But regularly, this height is a change. Okay? It means the velocity with time at the same position here at the exit is it changed according to a change of height. It means I can know what is this case, steady or unsteady direct. So this case is steady or unsteady? Unsteady. Why unsteady? Because h, it is not constant. It means the velocity not constant. It means all the time at the same cross section, at the same position, velocity changed with time. It means unsteady. Clear this? Okay. A flow through an expanding tube at constant rate is called, read carefully, then answer.
C, unsteady and uniform flow.
B.
and uniform flow.
C.
Steady and non-uniform flow.
D.
Okay,
Unsteady, non-uniform.
one by one. A flow through an expanding tube like this. Correct?
B.
Cross section x1, for example, at x1, this cross section at x2. As you see here, the diameter change, correct? We will know for continuity
Steady.
equations the velocity is directly
Steady and
just
non-uniform
proportional
flow.
with area. It means it's affected by diameter. It means the velocity with
Non-uniform.
change, correct? It means it is non-uniform, this one or this one. Correct or not?
Yes.
This is the first thing, expanding tube. Read continue. At constant rate, it means the velocity with time.
Steady.
It means steady. Clear? For all?
Yes.
Yeah, clear.
Laminar and turbulence flow. We start by describe what is laminar flow, and I tell you laminar flow, it is going to moving all together, all layers incoherent. Adjacent fluid layers move smoothly to each other. Okay, for example, this is straight laminar flow, this zigzag, but still all going moving together smoothly with respect to each other. What turbulence flow? Turbulence flow, it is not going to straight together like this. No, we have eddies, we have waves, everything same like this. It's going in this direction, laminar till here. But here we have some turbulence here moving and some circulations and something. It's not clear eddies and vortices like this. This turbulent flow. So it is motion of different sizes and intense cross-stream mixing this turbulence flow. Okay, here we can ask questions. Which is better for application? Hello?
This laminar.
I think we have other 15 engineers. Please share with us.
Hello. It's laminar.
Laminar.
Depends on the application.
Any more?
This is the turbulent.
Actually, one of the answers is it depends on application. I think this is the nearest one. Sometimes we prefer turbulent, sometimes we prefer laminar. I see laminar is better, not make eddies going straight, easy, is good, but for application or maybe many application. But some application we need turbulence and we need good turbulence, especially for anything we need mixing. Okay, so it depends on application. Okay. Viscous and inviscid flow. Remember the last session we studied what? We studied viscosity. This viscosity property is effect on the flow, and this one of the main property is going to keep or make difference between velocity of layers, velocity gradient. This is the main reason to create velocity gradient for the flow. It means if the flow have a viscosity, or mentioned to this one is viscous flow, it means the effect of viscosity is high. Effect of viscosity is high. So in this case, something like this we will found. It's called viscous flow. Viscous flow. You see the profile for the velocity, maximum at the center, and the decrease when going up and going down, because this is a tube. Tube, it means this one is stationary, this stationary side or stationary one. Is different for the example, the one example we solved it last session. A stationary plate at below and moving plate at above, it means the minimum at below and the maximum at above. No, here this is a tube, so the maximum at the center and at the walls, it is zeros. But in other case, the effect of viscosity in other one is almost null. So in this case, we will find almost this profile constant, even almost constant. While this area and this area is slightly affected by the viscosity, because it is have a big fraction between the flow and what? Between the flow and the wall. There's a big friction here. If we going to make zoom for this area, we'll find something like this. It's almost at the middle, it is a straight inviscid flow, but we're going to be near from the wall, we will find the effect of viscosity is big. Okay, because this near, or the shear stress, it is high for this area. Okay, and this area normally is called boundary layer. Boundary layer. Clear? Compressible and non-compressible flow. Compressible and non-compressible flow. Compressible flow, from the title of for each one, compressible and the non-compressible, it is directly relation between the pressure and the volume. If we apply a pressure, apply force, create a pressure, if this pressure not affect on the volume, it means this incompressible flow, incompressible flow, or incompressible fluid. But if we apply by force, create pressure, and this pressure make it change in a volume, this compressible fluid or compressible flow. So in this case, we will found gaseous type is almost compressible flow, because it's affected directly with volume, pressure directly affected by volume, inversely proportional. But normally for incompressible fluid, like almost all liquids, for all liquids, almost when we apply a pressure, the volume not changed, or slightly change. This clear? Okay. Check please.
C, compressibility.
C, compressibility.
Compressibility.
C.
Yes.
Correct. Rotational and irrotational flow. Rotational and irrotational flow. The main difference between rotational and irrotational flow, if the flow rotated, moving, and the particle inside rotated during movement of fluid or during rotational of fluid, this particles is rotated around own axis, same like hello, something happened. All hear me now?
Yeah, can hear.
All see screen or not?
Yes, can see the screen.
Screen shared?
Yes, yes.
Okay. Okay, now? Okay, again, for rotational and rotational flow is the fluid particles flowing along a streamline but rotate about their own axis. But if these particles of the fluid don't rotate about their own axis, this is irrotational flow. So the first one, this represents for irrotational flow, but the second one, this represents rotational flow. Irrotational flow and rotational flow. Okay, clear?
This will be laminar flow,
Which one?
rotational or and irrotational flow. Will it be laminar or
Not
it can be
related.
laminar or
Laminar or turbulent?
yes.
It's not related. Different classification. This is what I start for at the beginning. Different classification. It means I can classify the flow steady or unsteady, separate, uniform, non-uniform, separate, laminar, turbulent, separate, rotational, irrotational, separate, 1D, 2D, 3D, dimensional, separate, viscous, inviscid, separate, and so on. Okay?
Okay.
Different classification. Each one depends on what is the parameter affected for that. Here we study the flow. This particle is rotated or not rotated, and so on. Maybe laminar or turbulent.
Okay.
D, 1000
D.
centimeter cube.
D.
E, 1000 centimeters.
D, correct.
D.
What is one-dimensional flow?
B,
Straight
takes place in
line.
straight line.
Correct. When we can say this fluid is ideal?
D, inviscous and compressible.
No, both.
C.
Inviscous and incompressible. Inviscous and incompressible.
Incompressible.
Continuity equation. One of the equation, it is very important in the exam. Actually, the first equation here is general one, but we don't study and we don't go in details for this one because we don't use in the exam normally. But we just, I describe each term and then going to focus for the important terms in the exam. These three terms, what's the meaning first for continuity equation? Continuity equation is the conservation of mass. Conservation of mass. And the equation for this one, d by dt, mass controlled volume, plus sum of m dot out minus sum of m dot n equal to 0. It means we have think like this, and we have some parts like this. This in, this out, this out. The m dot out, it means all out, outflow, all mass flow rate out from the system we start. If the system, we suppose this system, for example, is a tank. Second one, m dot 1. M dot 1 is mass n, going to cross section here for the input. Last one, d by dt and control volume. What is this part? This is the mass it changed inside control volume with time. It means if this is the control volume, this is the system we study here. It means this area, it is the mass inside the control volume. This mass, if the input and output not equal, it means this one, it changed. It changed with time. Maybe increase, maybe decrease, according to which is higher, in or out. This makes sense, correct? So, in this case, we will find this have a value. But here, for regular problems coming in the exam, not ask for this part normal, and all the time almost 0. It means in this case almost all questions coming in the exam, the amount flow out shall be equal to the amount of flow in. Any mass going in should be going out. And the one of the main application for this, pipeline. Any pipeline, anything going in for pipeline should be going out. So m dot n equal m dot out, whatever the number of input and the number of output. As per the network, you know, if you have network for pipeline, at the end, sum of n equals sum of out. What is this? This is continuity equation, but with a special case, there is no accumulated mass flow rate inside. Okay, so in this application, we will find for pipeline, for example, sum of m dot n equal sum of m dot out. this one. M dot n or M dot 2 equal M dot 1. Applied for this example, for example. This one position, this two second position, M dot n equal M dot out. Okay. It means one of the important, this equation, M dot n or sum of M dot n equals sum of M dot out. What else? Second important thing here is what is M dot actually? This is a mass flow rate. Mass flow rate. Equal what? Equal rho here. Rho V A. What is rho? Density for the fluid. What is velocity? Velocity at this position. What is area? Area at this position. It is the same for other one. Rho A V. A special case for if the constant density here. If this fluid is constant density. Normally it is for all application of liquid. Normally if this fluid is liquid, not gas, normally the density not a change. So in this case we can cancel rho with rho, and the equation will be VA equal VA or AV equal AV. Correct? What is AV? AV is Q. What is it? Q. QN?
Mass flow rate.
Q out. This mass flow rate, this volume flow rate, this volume flow rate, this mass flow rate. If in the problem mention flow rate, that's it, should be check the units for this. This related to mass or related to density, because sometimes it is question coming asking for volume flow rate and sometimes asking for mass flow rate. Check by units. Also sometimes is mentioned for this discharge. That's it. Sometimes discharge represent for volume flow rate and sometimes discharge represent for mass flow rate. It depends on the units. Units used for example here for kilogram per second. This is the mass flow rate. Pound mass per second. What else? Sometimes something is called sludge. Something like sludge. I don't remember exactly. The sludge. Sludge per second. Something like that. For Q volume flow rate, we have a lot and many for this one used, especially for pressure. Meter cube per second is a regular order from SI. Sometimes meter cube per hour, sometimes centimeter cube per second, and so on. But regularly meter cube per second or meter cube per hour. But for British, we have CFM, cubic feet per minute. We have GBM, gallon per minute. We have FS, cubic feet per second.
LPM, liter per minute.
Yes, GBM, liter per minute. These different units for Q. Okay. Many question, again, at least one question coming for the exam for continuity. Regularly for each exam, I found one question for continuity. So this is very important. Sometimes the equation is not related for continuity direct, but it's support is a equation supported for the main equation used for the problem. Okay, so it is one of the important equations solved in the exam. Any questions for this equation?
Here the density means rho 2 and rho 1 is the same.
Here we cancel density because this flow it is constant density normally for fluids. But
Yeah.
sometimes if the question asks for gases, normally we use this one, and the question given M dot, not given Q. More questions?
If Q in is not equal to Q out, it is not constant.
No, constant. But what is constant? Not the value of Q itself constant. The constant is what is in must be is equal to out. For example, sometimes you have something like this. This one, this two. This two input and this out, this out, this out, this three output. At the end, Q1 plus Q2 as input equal Q3 plus Q4 plus Q5. It's clear now? Is this equation now clear?
Yes, Q1 plus Q2 equal to Q3, Q4, Q5 plus.
Yeah, because M equal out. Okay.
But I think he's asking if not same, Q in and Q out not same.
The number is not the same, two input and three output. No problem. But what is shall be the same? The flow rate itself, the total amount going in must be equal the flow going out.
Right.
Here?
Clear, sir, understood.
Okay. And this is the happy face here. Q equal AV. Okay, don't forget this one. Have a question? Okay.
Continuous.
An ideal
D.
flow of any fluid must fulfill the following.
D.
D. Continuity equation.
D, the density are equal. That's one of them. Is it?
Yes. Continuity equation. Second thing here, Bernoulli equations. Second important equation is exam. Bernoulli equation in easier definition, it is an energy equation. But Bernoulli equation is the ideal form for energy equation. Same energy equation, but in ideal form. It means we don't mention for losses or other things, only energy for the flow. This equation describes the energy along streamline. One of the main results for this equation is the total and or the sum of different type of these energies in the flow must be at the end equal to constant. Must be at the end equal to constant. Any particle during the flow have energy. If we check these particles and different particles, at the end should be these particles all the same, have the same energy along the streamline. This Bernoulli equation. But not important to have the same for everything inside. What's the meaning? This energy, it is the total energy for these particles. But this total energy is consist of three parts. One part is flow energy. Second part is potential energy. Third part is kinetic energy. The total should be the same from point to another. But what happened inside, do what you want. Maybe the flow energy for this point, it's not the same flow energy for the other point. So, by default, the potential or kinetic also change it to be at the end. The total energy for this point equals the total point for this point. It means this total energy at the end equal to constant. This total energy at the end is equal to constant.
Dr. Sami?
Yes, with you?
When you talk about constant at certain point, or are you comparing a different point in the system?
Yes, no. When we compare different points along the streamline.
Along streamline. And when you say constant, what do you mean by constant? I know constant is a number, but you mean the total of the
streamline? I study this point. I
Okay.
study this point. I study this point. The total energy here as a value is equal to the total energy here is equal to the total energy.
Okay, clear. Okay, thank you.
But what happened inside? Because the total energy here, it has three parts. Maybe one of this part is not found. Maybe this part, it's only coming from this flow energy and kinetic energy. No problem. This one, no. And this one, flow energy is less than the first one. So by default, kinetic energy is higher. To be at the end, total is constant.
You mean it's like conversion, the converted to different type of energy, but the total
Yes,
is constant.
converted
Okay.
from side to
Okay.
another.
Okay, cool. Thank you.
Clear? We present here this Bernoulli equation in different forms. What's the meaning of different forms? Different forms according to units. According to units. For example, I can represent energy equation, Bernoulli equation by energy form like this. Flow energy plus potential energy plus kinetic energy. It means the unit for each term, because this plus must be all terms the same have units. It means this term, it is a unit of energy, joule. This term, joule. This term, joule. Clear? And this one represented by joule. You remember B equal gamma H? This pressure equal gamma H, and I tell you this gamma is constant, and we have many devices measure pressure, but in a form of head. This is the same concept. What is this the same concept? This is a energy equation, but or Bernoulli equation, but in the form of energy form. Each term have unit of energy. I can represent this equation the same, typically, not different anything, the same, but in head form. It means the unit for this term is unit of head, like meter, for example. The unit of this is meter or feet, whatever. But at the end is unit of length. Also, this one is meter. Clear? And dimension for this two is piezometric head, and this one velocity head. This equivalent to this one, exactly typical, the same, not different. What? How to get this one from this one? Just easy. What happened? Just I divide G for each term. If you divide here G, cancel G with G, Z. If you divide here G, rho G is gamma, specific weight. If you divide here G, this 1/2G velocity square, V square over 2G. It means this is the same equation, but different units. Why we do that? Because same like the devices, for example, devices for pressure. Devices is measure what? But actually, it is measure head. It means just measure head, and this head represents a pressure value. If you know the fluid, you can know the pressure. Both is represent the same concept. This is the same. For the problems, it is easier to use this shape, head form, easier than to use energy form. So the regular equation used this one, B over gamma plus Z plus V square over 2G equal to 5. Okay, and the unit for each term is unit of length, meter, feet, and so on. We have another form, but not mentioned here in the slide, is a pressure form. We use it sometimes, but a little. This normally is not used, rarely we're going to use this one. Default, we use this one, this is a default. And sometimes we use a pressure form. So we need to write the pressure form to be aware also for this one. Where is it? I can write by this color. Okay, pressure form, it means should be the unit for each term is a pressure. It means we need to cancel this gamma. We need to remove it. Okay, so I multiply gamma for each term. Okay, proceed. We multiply gamma here, gamma cancels, gamma is a B. Plus, here, multiply gamma, it means gamma Z. Plus, here, multiply by gamma. When I multiply by gamma, gamma is rho G. G cancels with G, it means remaining rho. Correct? It means plus rho V square over, how can I write? Half rho V square, half rho V square, equal to what? The same constant. Now I write the same equation for these two, but in what? In pressure form. In pressure form. What is this term? P is a pressure. Gamma Z plus half rho V square, all unit of pressure. It means this Pascal, Pascal, Pascal. BSI, BSI, BSI. That's it. This two is mentioned for this two is the same here. Piezometric head, here piezometric pressure. Piezometric pressure. This one is piezometric pressure. This one is velocity head. This we can mention any of two. We can mention dynamic pressure. Dynamic what? Dynamic pressure. Excuse me, at the end we have B over gamma plus Z plus V square over 2G equal constant, and also B plus gamma Z plus half rho V square equal to constant, both the same. This, as mentioned for the slides, this what the piezometric head. This mentioned for static head. Plus this for velocity head. This mentioned for dynamic head equal total head. Equal what? Total head. This piezometric pressure, which is mentioned to static pressure, plus this one is dynamic pressure, and the constant is referred to total pressure. Check carefully and tell me it is okay for all.
Yes.
Any
it's
question?
okay.
No question? Going back to screen share.
So unit will be, excuse me, sir. Unit will be changed like in this meter, but actually the joule, the unit, energy for energy.
For the third one, Pascal, Pascal, Pascal.
Pascal, okay. This is the press for the pressure. But as per the first Bernoulli, this slide, rho P upon rho plus ZG, this is the unit joule.
Yes.
But as you tell me that after head, so head it will become the meter.
Yes, head is meter.
So the unit will be the in the meter or joule.
No. The second equation is a unit of head, meter, but still represent energy. The third one is unit of pressure, but still is represent energy. All the same, represent the energy for the flow, but represent the energy with different units. That's it. If you see with me at the end, what is the main factors cancel or multiply for every time related for density? If you check,
Density, yes.
Yeah, density.
And density is a property for the flow. So the three represent for the same thing. Clear?
Yeah.
That's it. Just G and the rho. That's it. Specific weight. It's a property for the material.
Yes.
Bernoulli equation is based on the assumption that
All of the above.
D.
all of the above. Correct. Euler's equation. Euler equation is the same used for energy calculation, same like Bernoulli. But Bernoulli, it's coming from one is called Lagrange approach. But here, this another approach is called Euler approach. This Euler approach, mainly the main factor not depend on the velocity. Almost the velocity used for Bernoulli is a constant or uniform velocity. Let's keep everything, it is almost static, even if it is moving, but we use it as it is. The effect of acceleration not appear in the equation. But for more practice, more applied application, Euler is better because the effect for acceleration, it is clear for this equation because the equation is including acceleration. But we don't going in details for this equation. It's not coming in the exam. I don't see before, and the equation itself, it is not applied easily. You can see the equation is very easy. Little parameters from the first one for Bernoulli, but it is not easy to substitution and understanding and apply. Bernoulli, it is easy. Just we know three parameters, three terms, one related to pressure, one related to velocity, one related to elevations. Just we check in the problem for the three, and all is scalar, no problem. This one not scalar. This is directionally. As the direction, it is effect on the problem. What is we going from the right to the left or from the left to the right, and we have a sign. This sign is effect, and so on. We don't go in details for this one. Static pressure, it is the pressure of the flowing fluid at any point. This is the definition for static pressure. Pressure of flowing fluid at any point. Same like piezometer. You remember the piezometer? Just the pipe above the tube. And this raising related to the effect of the pressure at the point. Pressure tape, it is a small hole in the pipe. Check this problem, please. Read carefully. This problem seem like exam questions with numbers, with figures, with everything. Just read carefully and we will solve it together. 1 minute to reading. Finished reading?